Hi, I'm Dr. Tony Schmitz. I'm a professor at the University of Tennessee, Knoxville, and joint faculty at Oak Ridge National Laboratory. The ACNC Machining Training Program is designed to teach essential machining skills and address the nation's growing manufacturing workforce gap. The in-person curriculum guides users through the steps necessary to set up and machine components. This program is unique because it introduces participants to the importance of considering machining dynamics when selecting CAM, or computer-aided manufacturing parameters. This leverages new technology advancements being developed now at Oak Ridge National Laboratory to increase productivity and efficiency of current machine tools. Thanks to a partnership with Oak Ridge National Laboratory, MSC Industrial Supply has deployed a new service called MillMax to provide tap testing in manufacturing facilities. This product enables CNC programmers to select stable machining parameters for increased productivity without expensive trial and error. Today we're going to do a chatter demonstration that will be composed of 3 parts. The first thing we'll do is measure the tool tip dynamics using tap testing. My colleague here, Greg Corson, will be doing the tap testing for us. Once we've identified the tool tip dynamics, we'll predict a stability map. Given that stability map, we'll select machining conditions. And we'll do 2 machining conditions. The first will be for chatter, and the second will be for stable machining conditions, and we'll hear and see the difference. The third part, we'll remove the workpiece from the machine tool and we'll look at it under a microscope so that you can directly see the difference in surface finish and why we want to avoid chatter conditions. Okay, so let's begin with the tap test. So Greg, let's start in the X direction. What you're going to see from Greg is the tap Okay, so now we see in the top figure the force that came from the hammer. So it looks like an impulse. We tapped the tool. What we see in the bottom figure in the red is the tool's vibration response. So when we tap it, it vibrates. We'll do a few of those averages and then we'll take a look at the frequency response function. Greg? One more. Okay, so what we can see on the screen now is 5 individual taps of the tool. So you see the 1, 2, 3, 4, 5 peaks, and then 5 responses due to those hammer taps. Now that we have that information, we can use our software to calculate the frequency response function. Okay, so what do we see now? Well, we see the 2 parts of the frequency response function. The top is what we call the real part, and the bottom is what we call the imaginary part. That doesn't mean one exists and one doesn't, it's just a mathematical term. And so it is this information which then enables us to calculate our stability map and select machining conditions that are either stable or unstable. But before we're all done, we now need to measure in the other direction. So in this case, Greg was measuring in the X direction on the machine. Now we want to measure in the Y direction. Okay, so the computer is awaiting the hammer tap. And we see the result looks similar, right? We see the hammer input, so that's the force that we tapped the tool with the hammer, and then we see the vibration response of the tool because of that hammer tap. Okay? Thanks, Greg. So now, like the X direction, in the Y direction, we have 5 hammer taps, 1, 2, 3, 4, 5, and the corresponding vibration response of the tool for each one of those hammer taps. And now we can look at the frequency response function from that data. So there we go. So now we have the real and imaginary part of that frequency response function, which describes the vibration in response to a force. And with the X and Y direction data, we can now generate a stability map. And we're going to see 2 versions of those stability maps here. On the right, we see a version which is axial depth of cut in the vertical axis and spindle speed in the horizontal axis. And what we see is a white zone where combinations of axial depth and spindle speed will give us stable cutting, which is what we want, and then a red zone where combinations of axial depth and spindle speed will give us chatter, which is what we don't want. Another way to look at that data is the MSC MillMax dashboard. So in this case, instead of showing the map that we just looked at, we have a speedometer. And that speedometer is giving us spindle speed in RPM, and then we have it marked off as yellow, red, and green zones. So the red is where we'd anticipate chatter, the green is where we'd expect stable cutting conditions, and yellow marks the boundary between those two. Okay, so we're going to complete cutting tests now for 2 cases. The first case is we're going to select a spindle speed and axial depth which gives us chatter. And so we can see in this case for 6,600 RPM, we're in the red zone at a 20 millimeter axial depth, and we're predicting chatter. The same is true for the MSC MillMax dashboard. We have 6,600 RPM programmed, 20 millimeter axial depth, and then the 3 millimeter radial depth, and we're predicting chatter. We're in the red zone, and so we would have an unstable cut in that case. Now, if instead we change our spindle speed to a stable condition, we can see that for the stability map, that would be the blue circle that we see, and then we can change the spindle speed here to the stable cut, which is 5,700 RPM in our case. And now we've moved into the green zone, and we would predict stable cutting conditions by the MSC dashboard. Okay, so let's now proceed to our cuts, and we'll be able to see and hear the difference. So now we're ready to begin our cutting tests. And as I mentioned, we'll do 1 cut for unstable or chatter, and 1 cut for stable machining using the parameters that we already identified using our stability map and the MillMax dashboard. So what Greg's going to do is first complete a tool change to move the tool that we already measured into the spindle. He's going to adjust the coolant lines so that we have the coolant pointed at the tool, and then complete our first cutting test, which is the chatter demonstration. Greg? Okay, so the cut we heard there was unstable. That was chatter. We'll next complete a stable cut, and you will hear the difference. Then we'll take a look at the surfaces that were machined to compare them. So the only change between those 2 test cuts was spindle speed. Okay, so now we've taken the part out of the machine. We have one surface which we made under chatter or unstable conditions, and the other surface that we produced with stable machining parameters. Let's look at chatter first. So we have a digital microscope set up here. The chatter surface is under the digital microscope, and we can see it here. What we observe is a very irregular surface finish. The height of these variations that we see is large. So we can turn this around a little bit and you can see the variation in that surface finish for the unstable or chatter conditions. Now let's flip it over and look at the stable condition. So now for stable cutting conditions, we see a very regular surface finish with small deviations in height and a better surface that we could then use on production parts. So let's recap what we saw. We performed a tap test in order to measure the tool's vibration response. We used that information to develop a stability map, and then we also saw the MSC MillMax dashboard that showed the same information. We used those plots in order to select stable and unstable or chatter machining conditions. We then completed machining tests to show stable and unstable or chatter. For those work pieces that under the chatter and the stable conditions, we then looked at those surfaces. And we saw the chatter had a rough surface and irregular, and the stable machining conditions gave us a smooth surface with a regular pattern. I'd like to thank you for joining us today. It's certainly our pleasure to talk about machining dynamics, and keep your processes stable. We'll see you later.